What is Bernoulli's equation? I'm considering a pipe and an incompressible fluid flows through it. The pipe is not uniform, has a varying diameter. This section of the pipe is wider, and this section is narrower. And the height also varies. Let ρ is the density of the fluid. In this section, let the pressure of the fluid is P1, speed of the fluid is V1, and the height is H1. And in this section, the pressure is P2, the speed is V2, and the height is H2. Bernoulli's equation states that P1 plus 1 over 2 rho V1 squared plus rho GH1 is equal to P2 plus 1 over 2 rho V2 squared plus rho GH2, where g is the acceleration due to gravity. In this video, you are going to learn how to derive this equation. To derive the Bernoulli's equation, I'm considering a volume of fluid from here to here. So this is our object. And I am going to use the work-energy theorem on this object. That is, the net work done on an object is equal to the change in kinetic energy of the object. So I am going to find the net work done on this object in a time interval delta t, and its change in kinetic energy in that time interval. To find the net work, we need to know what are the forces acting on this object. The fluid on this side exerts a force on this surface of the object that I call F1. This force is due to the pressure of the fluid P1 on this surface. Let the area of cross-section of this side of the pipe is A1. So F1 is equal to P1 times the area, A1. And the fluid on this side exerts a force on this surface of the object. I call that F2. This force is due to the pressure P2 on this surface. Let the area of cross-section of this side of the pipe is A2. So F2 is equal to P2 times the area, A2. There is also the force of gravity acting on the object. So the net work on the object is the sum of the work done by the forces F1 and F2 and the work done by gravity. Let us take the initial time as T1. The fluid moves. And after the time interval delta t, it arrives here. The time it arrives here is the final time, T2. Let this distance be L1. On this side, the fluid moved from here to here in the time interval delta t. Let this distance be L2. Let us find the work by the forces F1 and F2. In the time interval delta t, the force F1 displaces the object from here to here with a displacement of L1. The force and the displacement are in the same direction. So the work by F1 is F1 times the displacement, L1. The force F2 is opposite to the direction of motion of the object, so it does a negative work on the object. The work by F2 is negative F2 times displacement, which is L2, is equal to, now substitute P1A1 for F1, times L1, minus, substitute P2A2 for F2, times L2. Note that at the initial time T1, the object was the fluid from here to here. So at time T1, the object was part 1 plus part 2. The object moved. And at time T2, the object is part 2 plus part 3. So at the final time, the object lost part 1 and gained part 3. Since the mass of the object doesn't change, the mass of part 1 must be equal to the mass of part 3. Let the mass be m. Since we assume that the fluid is incompressible, its density remains the same. So the volume of part 1 must be equal to the volume of part 3. Let the volume be V. Part 1 is a cylinder with area of cross-section A1 and height L1. So its volume is A1 times L1 equal to. And part 3 is a cylinder with area of cross-section A2 and height L2. So its volume is A2 times L2 is equal to V. Now substitute V for A1 L1 and A2 L2. You get P1 times V minus P2 times V. This is the work done by F1 and F2. Next, we need to find the work by gravity. We know that work on an object by gravity is equal to the negative of the change in potential energy of the object. The change in potential energy is final potential energy P2 minus the initial potential energy P1. P2 is the potential energy of the object at the final time T2. Since at time T2 the object was part 2 and part 3, this potential energy is the sum of the potential energy of part 2 and part 3. P1 is the potential energy at the initial time T1. Since at time T1 the object was part 1 and part 2, this potential energy is the sum of the potential energy of part 1 and part 2. You can cancel out potential energy of part 2. You get potential energy of part 3 minus potential energy of part 1. Part 3 has a mass of m and is at a height of h2. So its potential energy is m times g times h2. Part 1 is at a height of h1. So its potential energy is m times g times h1. The work by gravity is the negative of this change in potential energy is equal to negative mgh2. Negative of negative is positive, so plus mgh1. Next, we need to find the change in kinetic energy of the object, which is equal to the final kinetic energy, Ke2, minus the initial kinetic energy, Ke1. The final kinetic energy of the object is the kinetic energy at time T2, which is the sum of the kinetic energies of part 2 and part 3. The initial kinetic energy of the object is the kinetic energy at time T1, which is the sum of the kinetic energies of part 1 and part 2. You can cancel out the kinetic energy of part 2. You get the kinetic energy of part 3 minus the kinetic energy of part 1. The speed of the fluid in part 3 is V2. So the kinetic energy of part 3 is 1 over 2m V2 squared. And in part 1, the speed is V1, so the kinetic energy is 1 over 2m V1 squared. This is the change in kinetic energy of the object. Now, let us go back to the work energy theorem. Net work done on the object is sum of these two works is equal to the change in kinetic energy, which is this. Now divide the equation by V. Divide out V and V. This V and this V. Mass divided by volume is density, rho. So substitute rho for m over V. Now, move this term to the left-hand side, and these two terms to the right-hand side. You get P1 plus this term is equal to P2 plus this term. This is the Bernoulli's equation. Thus we derived the Bernoulli's equation.